Welcome to the video. Today's topic of discussion is IQHE or integer quantum Hall effect. Here you will find one very interesting phenomenon where the electrical resistance of a conductor becomes quantized. Yes, it becomes quantized. That means it can take only discrete values, not continuous values, only discrete values. And the formula for which is means resistance RH, RH for Hall resistance. Hall resistance RH is equal to H by E square into 1 by N, where H is Planck's constant, E is a charge of an electron, and N is an integer known as filling factor. So N may be equal to 1, 2, 3, 4, 5, etc. Means only integer values. And for each value, the corresponding level is known as Landau level. Okay, so this is the mathematical formula for that quantized resistance. But in which case this happens? This is a special case where you will find this. The case is you have to take one 2D electron system, yes, two-dimensional electron system. Means in case of a thin semiconductor layer, if you take one thin semiconductor layer, then it becomes a 2D electron system. Of course, you have to take semiconductor, not normal conductor. For normal conductors, you won't get this effect, this quantum Hall effect or integer quantum Hall effect, because in case of normal conductors, the density of electrons are too high. Density of electrons is too high in case of normal conductors. Okay, and mobility of the electrons in normal conductors is low as compared to semiconductors. Means in case of semiconductors, electron density is low and mobility is high, and this is the requirement to observe this phenomenon, integer quantum Hall effect, right? That's why semiconductor is required. Normal conductor cannot be used here. One more thing, if you use a normal conductor for the same experiment, then in that case there will be problem in resolving the different Landau levels. Anyway, for the purpose of the experiment, only semiconductors are used, and it should be a thin layer. That means it should be it can easily be considered as a two-dimensional electron system. Right? So this is the condition. One more condition is there. Temperature should be very low as the temperature of liquid helium, which is equal to 4.2 Kelvin. That is known to you. And extremely strong magnetic field is required. Means typically in the range of several Tesla, right? So this is the condition. If this be your condition during your experiment, then you can easily see the effect which is known as IQHE or integer quantum Hall effect. So I have already mentioned the formula. Formula is equal to what? Formula RH is equal to H by N square, H by E square into 1 by N, where H is Planck's constant. So there is an involvement of Planck's constant in the expression for quantized resistance, which is equal to quantized resistance is what? How this is calculated? This is the voltage developed across a conductor in the presence of a perpendicular magnetic field. That means here the voltage developed, the current carrying through the conductor and the applied magnetic field all are perpendicular to each other. Just like x, y and z axis remain perpendicular to each other in case of a rectangular Cartesian coordinate system. Similarly here also, the voltage developed due to the Hall effect, okay, voltage developed due to the Hall effect, actually due to the Lorentz force, okay. Anyway, I am not talking about all those things here. So here the voltage developed, the current passing through the conductor and the applied magnetic field all are perpendicular to each other. So this way you are getting the voltage, and now divide that voltage divided by the current which is flowing through the conductor. So that voltage divided by the current gives you resistance. That resistance is known as Hall resistance. So what is the interesting thing here? Yes, we are getting Landau levels, we are getting this quantized resistance. Is there any practical use of this? Yes, quantized resistance, this is used for international, this is used as an international standard for resistance measurement. Again, in case this has paved the way for topological insulators, and in the advancements of quantum computing systems, this is used, this concept IQHE. One more thing, in case of, I have already mentioned that the system, the arrangement, it is a two-dimensional. So if there are imperfections inside the material, then there is no problem at all. Because due to the quantum effects or due to quantum mechanics, the imperfections have no effect on the conductivity of the material. Electrons mainly flow or pass along the edges of the conductor, and they remain unaffected by the presence of impurities within the material. So this is a kind of special state known as edge states. In this case, edge states. So here the dominating role played by what? It is played by quantum mechanics. Okay, and that is why this is called a case of perfect conductivity. Means these can be considered as perfect conductors. Electrons flow only along the edges of the conductor. Okay, that's why this is said that way. But this is not superconductor. Okay, that is another concept. Don't get confused with superconductor. These are perfect conductors, not superconductors. And I have already mentioned that only semiconductors we have to take for the experiment. Okay. Otherwise, the quantum mechanics won't be able to dominate. Here in this case of semiconductors, quantum mechanics is playing the dominant role. It is dominating over other factors. But in case of normal conductors, quantum mechanics won't be able to dominate over other factors. Because in case of normal conductors, electron density is very high and mobility is low. Right? Anyway, so this was all about the topic IQHE, means integer quantum Hall effect, and this has practical applications. This is being used in the advancement of quantum computing systems, again for topological insulators. This concept is used, IQHE, and this discovery led to several developments, and the physicist who discovered this phenomenon in the year 1980, he won the Nobel Prize for this discovery. The name of the physicist is what? It is Klaus von Plissing. Right? Anyway, so this was all about today's topic, IQHE. Okay? So this is the end of this video. Thank you. Thank you for watching this video.